Okay, 8th and ninth grade. This is the lesson that you would normally have done on Monday, and because of the test, I'm giving this lesson for today, which will be Thursday. I'm giving you a lot of leeway here. If you don't want to do this lesson, you want to wait till the weekend when you come and pick up your test, and then you want to do your tests on Monday, and you want to do this lesson on Monday, that's fine. If you don't want to start the next model, you don't have to until after you take the test. That was my bad that I didn't have your test in your packet last week. I do have it there now, so you will be ready to take that test anytime you come. So anyhow, I will start with model 14 today. We will talk about the sounds and waves, and we'll do from 341 to 351. So that's a pretty big section. It's actually two parts, but there's not a lot of work. So I will also put on a video, and it will be the video for today, and it's little clips. They're kind of but if you want to watch them, I have videoed them, and so I'll put that on a separate video, and it will say 8th and ninth science videos. So here we go. If you're on 340, tell me about waves, okay? First thing when you think of waves, you think of water. Well, if you know anything at all, then you say, oh, I remember science waves. Oh yeah, I think of maybe light waves, or maybe sound waves. That would probably come to your mind first. Waves are just a term to describe energy. So when you think of waves, you think of water like the picture, and you'll see that on the video. Really, it's a transfer of energy is what wave does. If you turn over to 341, we'll talk about transverse waves. They are waves that look like this. Okay? And you will talk about a crest and a trough. That's not hard. The trough is in here, and the crest is up here. I mean, how much simpler can you get? Then you talk about a wavelength. When you talk about a wavelength, that is from one point to the next point. So this right here would be a wavelength. And depending on the sound, depending on what's making a wave, water, the wavelengths can be apart. You know how sometimes the waves come in just a little, real fast at the shore, and sometimes there's a big wave, and then it's another big wave, and they just come in far apart, but they're big. Okay, sound is no different. Anything like sound or light the same way. The crest is a high, the trough is a low. Like I told you, there is about 1, 2, 3, 4, 5 black words on the first paragraph there on 341, and they're black for a reason, because they're important. So I talk about crest, trough, and wavelength. The other one is the height of the wave is called amplitude. Now, you've been around electronics enough. If you've seen it, screen somewhere where somebody is running a microphone, you'll see it go, and the louder it is, the higher up it shoots. Now, I'm sure you know what I'm talking about. That's the amp, that's the amplitude. And then, that's how high this wave goes. So, if you had a little wave here, a little wave, choo, a little wave, you know that this one here has a lot more amplitude. Now, that's a poor excuse, but you know this tall one had more amp. And then, the next one is frequency. That's how many waves hit per second, frequency. And so the frequency could be like this, or they could go like this again. And when they're real close together, that means more of them hit per second. When you say frequency, that is always how many waves hit you per second. Or if you'd be standing in the water, the frequency of the waves is how many come crashing in and hitting you when you're standing there. I think I'll drop down to the little formula down at the bottom. You have a little, or it's in the middle of the page there. It's F equals V, and that looks like an H. It's a funny little H. That formula is something that we will be using. So if you want to know the frequency, okay, the F stands for frequency. And then you have V, and then that funny little H, if I can make it. Okay, the V stands for, this is frequency, and the V stands for speed. I'll put speed here. And then the H stands for the length. Okay, to find the frequency, you have speed over length. And that H is actually a word that means, let's see if I can say lambda. Lambda is the way it looks like it's spelled. You have seen that little symbol. You know, in math, sometimes we got this little symbol right here. Don't that look a little bit similar? Well, this is a symbol. Well, yeah, you know, well, you can just barely see in the video. That's a symbol for pi. Okay, that's a Greek word. This H is also a Greek word. Thought that was interesting. They both have the little whoop, a little tail to start out with. Or it's not an H, sorry, I'm calling it H. It's called lambda. Lambda. And I don't even know, it just looks, it's lambda, so lambda is the way I'm saying it. It's a lowercase Greek letter, and it represents wavelength. And then Hertz. The next black word I see is at the bottom of the page, 342, is Hertz. It is abbreviated HZ, and it's in honor. I thought this was interesting. I didn't know where Hertz come from. I've heard of sound Hertz or wave Hertz, and I didn't know that it was in honor of Hendrik Rudolf Hertz, and he was the man that discovered radio waves. Turn over to 342, and I will talk about, well, no, I've got the definition there. I should talk about transverse waves. That's what we've been talking about, is transverse waves. And you got the definition: a wave with a direction of propagation that is perpendicular to its direction of oscillation. Now, he says, that's a mouthful, isn't it? Actually, this definition is rather simple. Once you get past the $20 words, the word propagation just means travel. Okay, so that's pretty easy. For example, suppose that you and your friend stretch a tight rope between you. Then you flick the rope. So you've done this already. If you're waiting, hurry up, get a hold, you go flip, and then you see the waves go like this here on the rope. Okay, that is the travel, the propagation. And then that is how big, you know, the more you give the rope, the bigger you can make those waves, and then they'll go to the end, and that's the speed. So if you put that together, you have the oscillation of the wave. So that's a wave that moves horizontally toward the friend. Oscillation is moving this away, and the propagation is how big a humps you got in it. If you have lots of rope, you can make those humps go big. If you just have a little bit, you go like this here, and they just go real quick. Yeah, read that there. Now the next wave I want to talk to you about looks like a slinky. I think you know what a slinky is. And it's longitudinal. Now, I'm not sure if I got all those words. Longitudinal. And it's the next word, transverse wave, and then longitudinal wave. Now, please don't hold me to that pronunciation. A wave with a direction of propagation that is parallel to its direction of oscillation. Okay, so you take a slinky and he goes like this. Okay, instead of going up and down like this, you take a slinky, you fasten one in, and you give him a shove, and he goes. Well, this is called, instead of called wavelengths, instead of called crests and troughs, we call these compressions and ratification. Okay, it's compress, ratify, compress, ratify, compress, ratify is the wave movement. You got a good figure there of how that works. Yeah, again, just keep that. Compressions and ratifications are always with the longitudinal wave. I think I am ready to get over to example 14.1 on 344, and we're going to do a little math problem here. If you look on that page, on that number, top there, you'll need to figure this with me. And it says, what is the frequency of a wave that travels at the speed of 3 meters per second and it has a wavelength of 0.5 meters? Okay, so we're going to use this formula, 3 meters per second, and it has 0.5 meters. Remember, even though we use the symbol V for equation 14.1, it means speed. Since we are given the speed and the wavelength, and since the units are consistent, both distant units are meters, okay? So we're working with meters here. We don't have to worry about switching from one to the other. We can just plug numbers into the equation and get the answer. So we got 3 meters per second, and it's 0.5 seconds. So you put 3.5. Okay? And now we want to know how many to find the frequency. So we simply go to 0.5 divided by 3. So I would go, that equals 6. B1 would be, see, this is actually just a half. And so our frequency is 0.6. And that is my Hertz, or my HZ. Okay, put your seconds and your speed. Your speed is 3 meters, and the length is 0.5. So the wave is going 0.5, and it's traveling. It's going up and down 0.5, 0.5, up and down. And then the speed that it's going is 3. The speed is 3 meters. I'm going to just abbreviate it, meters per second. So you put the speed at 3 meters per second. The rope is going 3 meters per second, and it's going up and down 0.5. You'll get to figure more of those as you go along. I'll let you, on your own, I'll let you do 14.1. 14.2, you're going to use this formula right here. And you're going to put that in that formula and figure it. If you have tenths, figure it with your tenths, or yeah. Now, let me go to the next one, and we'll talk about sound waves. And sound waves is what you've been listening to all morning here. As you listen to me talk, you've been hearing sound waves. You got medium. The black word is medium. And for an ocean, the medium in the energy is water. But for sound waves, it can be water. There can be sound passed and water can be the medium. But basically, it's the air that moves the sound waves along. So you should look at your examples in the 14.1 example. I don't know if you can do that. Oh yes, you can do that, but it'll be a little more work. 14.2 is very easy. You should be able to do that one with a pan and rice. Be sure to do that with a spoon. You will want to do that. So I will let you do the experiments if you have time to do all of them, but I want you to do the one with rice where you tap the pan. Let me see here. In sound waves on page 346, you have the picture of the ear. And the ear is making that sound, it is structured, and look at how the sound waves come from the mouth into the ear, and it's a pushing, just like your experiment when you did the rice bouncing. Oh, I didn't tell you what happened. But when you did the experiment, so rice moved on there, that's what's happening in your ear. When those waves go in your ear, it's a pushing on your tympanic membrane. Your tympanic membrane goes back and forth, back and forth, back and forth. Yeah, sounds and longitude waves. I don't know that I will have much to say. You read that part. Go over to, I want you to get the formula on 14.2, how to figure the sound of distance. And we talked about this in earlier unit about the sound of thunder. Well, we're going to figure it exact now. Instead of partially, this is an exact figure. And they have an experiment where you're supposed to do with a friend that's like 900 feet. If we were here, we would maybe do that out here in the school ball field. We'd probably have to start out by the road and go back past the cemetery to do that sound of the rock hitting. I've seen it already where a neighbor man was chopping wood, and he would chop down, and you could see him come back up, and about the time the axe got up to his head, it would look like, you would hear the sound. So it would look like he was hitting his head, and you hear boom, and then you go down, hit, and then as he come back up, it go boom. Now if he's far enough away, that will work perfectly. Well, that's what you're doing with hitting the rocks together as well. Your sight sound travels slower than light, if you want to use that term. Okay, on the next part, I will explain how to do that math equation. You will figure, you will use the distance of, the distance traveled is always 331.5. You can look at your example there on 14.3. And talking about the lightning, I will erase this. 14.3. 331.5 is always the figure plus 0.6 times the degrees. Sound travels different depending on the degree of the temperature. Now, this is getting very technical, okay? So what you have, 331.5 plus 0.6 times, and I put a dot there, times the degrees, and it has to be Celsius degrees. Let's say 20 degrees, I think is the example he uses in the book. Yes. So you multiply 6 times 20, 0.6 is 0, 2, 6 is 12, and your decimals here. So once you times these two together, you have 12. So now you take 12 plus this. So 12 is 5, 3, 4, 3. So it's going to be 343 meters and a half. 343 and a half meters. This is basically the speed that sound will travel. He was specifically talking about lightning. So what I'm going to just help you with number 14.3. It's on top of 251. What's the speed of sound and air when the temperature is 28 degrees Celsius? Okay, how fast will it move when it's 28? Okay, it's not any difficult. I won't have to erase much. You have your 31.5 plus 0.6 times your Celsius degrees. So I have to go 0.6 times 28. Whoa, I'm just about off the camera. Let me turn that just a little bit to help you out. There we go. 6.6 times 28. So I got 28.6. Whoa, I'll get the answer off again. Well, I have to keep it up here then. 0.6 times 28. 6 eighths is 48. 2 sixes is 12. Plus 4 is 16. 16.8. If I did that, 6, 3 sixes, yes, 16.8. Now I have to add this. You see, this is addition, so I add this here. First I multiply those two together. I come over here and add 5 and 8 is 13. 6, 7, 8. Better put my decimal there. 348.3 meters. That's always meters. All right. Again, you work on this at your choosing. If you want to finish the test on the weekend first, before you do this lesson, I'll sure you have the time to do that. And you will also have a video to go with this lesson.